In that case, the laws of physics may differ from universe to universe, resulting in drastically different conditions of existence. Exploring the implications of multiple universes of varying sizes expands our understanding of the cosmos and challenges our perception of reality itself. It promotes discussion about the nature of existence, the fine-tuning of physical laws, and the potential for alternative life forms in the larger landscape of the multiverse. The prospect of other universes with dimensions configured in ways we cannot currently imagine fascinates scientists and philosophers alike, inviting further investigation into the very essence of the universe in which we live. Another intriguing idea related to the Big Bang is the theory of cosmic inflation. Proposed in the 1970s, this theory suggests that in a very brief moment, less than a trillionth of a second, the universe underwent an exponential expansion. This rapid inflation helps explain the uniformity of the cosmic microwave background and the large-scale structure of the universe we observe today. By smoothing out any irregularities, inflation solves why the universe looks nearly uniform on a large scale. Some alternative theories have emerged that challenge or seek to extend the Big Bang model. The cyclic model, for example, states that the universe undergoes endless cycles of expansion and contraction, with each cycle leading to a new Big Bang. According to this view, the universe has no ultimate origin or end, but exists in an eternal rhythm of birth and rebirth. This model has intriguing implications for understanding concepts such as time and entropy. Additionally, string theory offers a different perspective, suggesting that our universe is just one of many in a larger space. In this structure, the interaction of fundamental strings can lead to the creation of many universes, each with its own distinctive properties and laws of physics. This multiverse view raises questions about the nature of reality and our place in the vast and potentially infinite cosmos. As scientists continue to explore and collect data, our understanding of the origins of the universe may evolve further, potentially leading to revolutionary ideas that deepen our understanding of existence itself. Each theory, established or new, contributes to the complex tapestry of ideas that shape our quest to unravel the mysteries of the cosmos. Cosmic rebirth theory, often associated with the cyclical model of the universe, suggests that the cosmos undergoes endless cycles of expansion and contraction, leading to a kind of eternal renewal. In this framework, the universe has no single beginning or end, but instead exists in a continuous process, where each cycle begins with an event similar to the Big Bang and ends in a collapse, sometimes called the Big Crunch. In its basic form, the theory suggests that after an expansion phase, the universe eventually reaches its maximum size. At this point, gravitational forces may become dominant, causing the universe to contract. This era of contraction will cause all matter to converge, eventually creating the conditions for a new singularity very similar to the one theorized to have existed during the Big Bang. From this special state, a new expansion can begin, marking the rebirth of the universe in a cycle that can repeat itself endlessly. This concept addresses some intriguing questions in cosmology, such as the nature of time and entropy. In a cyclical model, time would not be linear. Each cycle could reset conditions, potentially recalibrating the entropy of the universe. However, critics point out that during each cycle, the universe's entropy tends to increase, raising concerns about whether the universe will be able to transition smoothly from collapse to new expansion. If the expansion continues, the effects will increase. Stars inside galaxies can feel the strain from this accelerated expansion. Over time, the gravitational forces that keep individual stars together will not be enough to resist the increasing pull of dark energy. Eventually, stars will lose their gravitational pull, causing their structures to collapse. This dramatic expansion will progress even further to affect solar systems and galaxies, tearing apart planets, moons, and other celestial bodies. Eventually, even the atoms and subatomic particles that make up matter can be torn apart, leading to a universe in which all forms of structure disintegrate under the stress of the relentless thrust of dark energy. If the Big Rift unfolds as described, it will culminate in an event where, at some point in the future, all matter in the universe is completely torn apart, reducing it to its most fundamental components. This scenario raises profound questions about the nature and properties of dark energy, prompting scientists to investigate its fundamental role in the cosmos and how it affects the ultimate fate of the universe. As research progresses, the effects of the Big Dipper continue to shape discussions about the long-term evolution of the universe, inviting further exploration of the mysteries of cosmic forces. Boltzmann's brane hypothesis emerges from the field of statistical mechanics, proposing a thought experiment regarding the nature of consciousness and the universe. He argues that, given the vastness and infinite potential of the universe, it is statistically likely that a single brane would spontaneously form in a state of chaos, complete with false memories and representations. This hypothetical brane would arise through random fluctuations in a high-entropy environment. The implications of the Boltzmann brane hypothesis are profound and challenge our understanding of reality. If such a brane could exist simply by chance, then it raises questions about the reliability of our own existence and consciousness. The universe we perceive may just be a fleeting, random arrangement of particles, while real existence may be far more chaotic and unstable than we imagine. This thought experiment intersects with cosmology, particularly in discussions of the nature of time and entropy. This means that as the universe continues to expand indefinitely, low-entropy regions may become increasingly rare. This could eventually lead to a scenario where Boltzmann branes become more common than actual conscious observers, fueling philosophical debates about the nature of knowledge and existence. As we consider our place in the cosmos, Boltzmann's brane hypothesis serves as a stark reminder of the complexity and entanglement of the universe. It challenges the notion of reality and pushes us to explore our understanding of consciousness, existence, and the underlying laws that govern everything around us. String theory offers a groundbreaking foundation in physics by suggesting that the fundamental building blocks of the universe are not point particles, but tiny, vibrating strings. One of the most fascinating aspects of string theory is its requirement for additional dimensions beyond the usual 3 dimensions of space and 1 dimension of time. Depending on one's version of string theory, these extra dimensions can range from 6 to 11, greatly expanding the dimensional landscape of our cosmos. Earth is about to get a new guest in its space neighborhood, but this is no ordinary flyby. Imagine a small rock the size of a house circling the Earth for a couple of months before waving goodbye and continuing its journey around the Sun. This is the story of 2024 PT5, a small asteroid that is set to become Earth's temporary mini-moon for about 50 days, starting in late September 2024. In this video, we'll explore what makes this mini-moon so special, delve into the science behind its temporary takeover of Earth, explore the implications of such events for protecting the planet, and see what we can learn from studying these fleeting space visitors. Discovered in August 2024 by the Atlas Asteroid Collision Warning System, 2024 PT5 is a small asteroid about 10 meters in diameter that has been identified as a potential mini-moon for Earth. Atlas is a state-of-the-art automated system designed to detect asteroids that could threaten our planet. Its rapid detection allows astronomers to quickly calculate the asteroid's path and assess potential risks. In the case of 2024 PT5, the analysis revealed the unexpected and encouraging news that this small asteroid is not on a collision course with Earth. Instead, it will be briefly captured by Earth's gravity, turning into a temporary mini-moon. What makes it particularly interesting is its size and trajectory. At only 10 meters across, it is relatively small compared to the larger asteroids that often make headlines. However, it is this small size that makes it more susceptible to temporary capture by Earth's gravity. Unlike larger asteroids, which fly past Earth at high speed and continue their orbit around the Sun, smaller objects like this one can be caught by the gravitational tug-of-war. This tug-of-war results in a temporary capture, creating what is often referred to as a mini-moon. This asteroid probably comes from the Arjuna asteroid group, which consists of small asteroids with orbits around the Sun very similar to Earth's. These asteroids, due to their proximity and orbital patterns, are more likely to fall under the gravitational pull of Earth. Scientists have determined that 2024 PT5 is a natural object, not space debris, which is important because it means that its trajectory is not affected by the forces that affect man-made objects in space, such as solar radiation pressure or atmospheric drag. This natural orbit makes it an ideal candidate for a temporary mini-moon. Understanding the nature of 2024 PT5 is critical for several reasons. First, it provides a rare opportunity to closely study a near-Earth object, even if only for a short period. Second, such events serve as valuable test cases for improving our asteroid detection and tracking systems. When we talk about Earth capturing an asteroid, we're really talking about a delicate balance of power. In particular, the gravitational attraction of the Earth and the Moon combined with the speed of the asteroid itself. One possibility is that the geometry of higher dimensions may affect the behavior of gravitational waves. These waves, caused by catastrophic cosmic events such as black hole mergers, crisscross the fabric of space-time. If there are additional dimensions, they can provide new paths for these waves, affecting their propagation and detection. This could improve our understanding of cosmic events and enhance our ability to observe phenomena that were previously unavailable. Given the expansion of the universe, these extra dimensions could also change our understanding of dark energy, the mysterious force driving the universe's accelerated expansion. If higher dimensions interact with known forces in unexpected ways, this could lead to different effects on the rate of cosmic expansion and potentially shed light on the nature of dark energy itself. By exploring how these extra dimensions connect to our own, scientists could find ways to explain the accelerating expansion of the universe. In addition, higher dimensions can affect fundamental particle properties, contributing to variations in particle behavior at extremely high energies, such as in cosmic rays or particle accelerators. These effects may shed light on the unification of fundamental forces of nature, providing a path to a more comprehensive theory of physics. Ultimately, exploring the implications of higher dimensions encourages a re-evaluation of our understanding of the universe, opening the door to new theories and vast possibilities. The concept of compact dimensions arises in string theory and other higher dimensional theories, where additional spatial dimensions beyond the familiar three exist, but are not as easily observed. These dimensions are said to be compacted, meaning they are compacted into extremely small, intricate shapes that are often described mathematically as polymorphic structures. Because they are very tiny, typically on the Planck scale, they remain undetected by modern experimental techniques that probe only subatomic scales. The existence of compact dimensions has significant implications for how we understand the fundamental forces of nature and the particles that make up the universe. In this framework, the specific topology or shape of compacted dimensions affects particle properties such as mass and charge. Different compactifications can lead to different physical scenarios, potentially explaining why some particles appear in our universe and others do not. Each unique compaction has its own set of fundamental particles and interactions, suggesting that the characteristics of our universe may be shaped by the way these extra dimensions are configured. Moreover, compact dimensions may also play a role in determining the fundamental constants that govern the universe. Because these measurements can produce a variety of physical landscapes, they can contribute to the so-called landscape problem in string theory, in which there are a large number of combinations, each leading to different physical laws. This raises interesting questions about the anthropic principle and why our universe seems fine-tuned for life. Could it be that we are simply in one of the many possible configurations of compacted dimensions that allow for such a diverse range of physical phenomena? Finally, when the compact dimensions interact with known forces, it can provide new physical predictions. For example, gravitational interactions can extend to these hidden dimensions, changing our perception of phenomena such as gravity and its behavior at different scales. The study of compact dimensions continues to pose intriguing challenges, pushing the boundaries of our knowledge and offering a window into the mysteries that govern the fundamental structure of reality. Gravity in higher dimensions operates according to principles that may differ significantly from our familiar three-dimensional understanding. In the context of general relativity, gravity is described as the curvature of spacetime caused by mass and energy. When we extend this framework to higher dimensional space, gravity not only affects the three spatial dimensions we perceive, but also interacts with additional dimensions, creating fascinating complexities. In higher dimensional theories, such as string theories, the presence of extra dimensions can change the behavior of the gravitational force. For example, gravity may be much weaker in higher dimensions than in lower dimensions. This is because in a five-dimensional scenario, gravity can spread out more, reducing its strength. This characteristic may help explain why gravity is much weaker compared to other fundamental forces such as electromagnetism, potentially providing insight into the hierarchy problem in particle physics. Moreover, the geometry of the extra dimensions can affect gravitational waves, which are ripples in space-time generated by the acceleration of masses. Like any wave traveling through a medium, gravitational waves can cut through these higher dimensional spaces in unique ways, resulting in different propagation and interaction characteristics. Such effects could become observable in experiments designed to detect gravitational waves, providing a potential means of studying the nature of higher dimensions. Additionally, gravitational interactions with compacted dimensions can lead to phenomena such as gravitational leakage into these hidden dimensions. This may explain why we perceive gravity differently than other forces, and may also have implications for the dynamics of our universe. Theoretical studies of these complex interactions not only challenge our current understanding of gravity, but also reveal ways to unify nature's fundamental forces, illuminating the intricate web that connects the universe's dimensions. The concept of multiple universes existing in different dimensional configurations is a fascinating idea that stems from theories such as string theory and the multiverse hypothesis. In this framework, it is assumed that universes can arise from different mechanisms or compactifications of higher dimensions, resulting in an almost infinite variety of physical realities, each with its own set of laws and constants. These alternate universes may have their own properties, initial conditions, and even different forms of matter and energy. Each universe may exhibit certain dimensional characteristics that will affect fundamental forces and particle behavior. For example, in a universe with more compacted dimensions, the interactions between particles may be very different from the interactions in our familiar three-dimensional space. This variability opens up a wide range of possibilities, where some universes may allow complex structures and life, while others may lead to completely different physical phenomena, potentially producing unrecognizable forms. The idea of distinct dimensional configurations also raises philosophical and scientific questions about the nature of reality. If these universes coexist, they may be completely separate and isolated, making them impossible to detect. This is consistent with the multiverse interpretation of quantum mechanics, suggesting that each quantum solution branches out to create different realities in a vast multiverse. Various versions of the theory of cosmic rebirth have been proposed to solve these problems. Some versions offer additional mechanisms to counteract the increase in entropy, combining complex ideas from quantum mechanics and string theory to specify how each cycle can occur. Moreover, these models emphasize the possibility of new physical processes or phenomena occurring with each cycle, which may lead to different physical laws or states in the reborn universe. As our observational tools and theoretical framework develop, researchers are cautiously exploring the implications of cosmic rebirth. While the notion of an eternal universe challenges traditional understandings of beginnings and ends, it opens exciting avenues for further investigation into the very nature of existence, time, and the structure of reality itself. The Big Freeze is one of the leading theories about the ultimate fate of the universe, based on the observation that the universe is expanding at an increasing rate. This concept is also closely related to the behavior of dark energy, the mysterious force that drives the acceleration. In this scenario, as the universe continues to expand, galaxies will gradually drift apart over vast stretches of time, cooling and transforming the cosmic landscape. As the stars expand, they will begin to exhaust their nuclear fuel. In 1 to 2 trillion years, most of the stars will have burned out, leading to a universe filled mostly with white dwarfs, neutron stars, and black holes. The stellar objects that remain will be dimmer and hotter at first, but eventually fade into cold remnants. Over an incredibly long period of time, the light and energy produced during star formation will have greatly diminished, leaving the universe in a dark, cold state. During the Big Freeze, the temperature of the universe will approach absolute zero as the galaxies recede into the vast void of space. Quantum fluctuations may still cause random interactions, but the overall space environment will become increasingly desolate. This final state, characterized by the absence of significant energy sources, means that life as we know it will become impossible, and any remnants of systems that were once active will undergo further degradation. The Big Freeze is a scenario devoid of significant physical activity, representing a universe that becomes cold and lifeless. Although far from over, studying the Big Freeze adds depth to our understanding of the long-term evolution of the cosmos and forces us to grapple with profound questions about the existence and nature of time. As more data is collected and our understanding of dark energy improves, the scientific discourse surrounding various end-of-the-universe scenarios, including the Big Freeze, will continue to evolve. The Big Bang scenario is a hypothetical outcome of the end of the universe, based on the assumption that dark energy continues to accelerate the expansion of the universe at ever-increasing rates. If the effects of dark energy increase over time, this scenario suggests that the repulsive force of dark energy may eventually overcome all forms of gravitational attraction. Initially, the galaxies will continue to move away from each other, similar to the Big Freeze scenario, but the rate of expansion will accelerate even more. As dark energy builds up, it will begin to affect the structures of the galaxies themselves, causing them to move away at ever-increasing speeds. At some point, the gravitational bonds that hold galaxies together will weaken, causing disruptions in galaxy clusters. For this mini-moon, the conditions are just right for it to be captured by Earth's gravity for a short period, making one complete revolution around the planet in 50 days. When such an asteroid approaches Earth, it enters a region of space where the gravitational attraction of our planet begins to dominate that of the Sun. If the asteroid's speed and trajectory match perfectly, it can enter a temporary orbit around the Earth. However, unlike our permanent moon, which is in a stable orbit, These mini-moons are often in highly elliptical orbits, and their existence is fleeting. Current predictions for 2024 PT5 suggest that it will be captured by Earth's gravity in late September 2024, complete a single orbit around our planet, and then return to its orbit around the Sun by mid-November. The phenomenon of mini-moons, although relatively rare, has been observed several times, each of which has provided unique insight into the nature of small near-Earth objects and their interaction with our planet's gravity. One of the most well-documented cases was 2006 RH-120, a small asteroid that orbited Earth from 2006 to 2007. This mini-moon had a diameter of 3 to 6 meters and was in the sphere of gravitational influence of the Earth for about a year. This was an important event because it was one of the first times that astronomers were able to track the orbit of such a small object in real time, giving them unprecedented insight into the dynamics. Another notable example is 2020 CD3, which was discovered in 2018 and remained in orbit around Earth until 2020. This mini-moon was slightly larger than the 2006 RH-120 and was estimated to be about 1 to 2 meters in diameter. Its capture provided valuable data that helped refine models of how small objects interact with Earth's gravity. These past occurrences of multiple satellites have contributed significantly to our understanding of near-Earth objects. They showed that Earth's gravity can temporarily capture small asteroids, causing them to orbit briefly before continuing their journey around the Sun. This process is critical to understanding the potential risks associated with near-Earth objects, as it highlights the dynamic nature of these small bodies and their potential to approach Earth closer than originally predicted. Moreover, these studies allow us to look into the possibilities of future research and use of near-Earth objects. Mini-moons, like 2024 PT5, provide a unique opportunity for future space missions to study these small bodies up close, offering insights into their composition, structure, and potential resources. A better understanding of mini-moons could also help in planning missions aimed at mining valuable materials on asteroids or even in developing new technologies to deflect asteroids and protect the planet. Thanks for viewing. As we continue to explore and study these fleeting visitors, we are unlocking new mysteries of our cosmic neighborhood and developing better tools to protect our planet from potential threats. The story of 2024 PT5 is a reminder of the dynamic and ever-changing nature of our universe. The dominant theory of the origin of the universe is the Big Bang theory, which suggests that the universe began as an infinitely hot and dense singularity approximately 13.8 billion years ago. According to this theory, there was a rapid expansion that initiated the cooling process and allowed the fundamental particles to form. This expansion is still ongoing, and today we observe it as the redshift of distant galaxies. The cosmic microwave background, the faint afterglow of this early expansion, provides a key piece of evidence, providing a snapshot of the universe roughly 380,000 years after the Big Bang. The implications of these additional dimensions are both profound and staggering. These sizes are considered compacted, which means they are packed so tightly that they are invisible on conventional measurement scales. However, their existence could fundamentally change the laws of physics as we understand them. For example, the properties of fundamental particles, including mass and charge, can be affected by the shape and size of these hidden dimensions. As such, they may hold the key to unifying all fundamental forces, including gravity, within a single theoretical framework. Moreover, the existence of extra dimensions can open up explanations of unresolved questions in physics. For example, they could offer insights into the nature of dark matter and dark energy, the mysterious components that make up most of the mass energy of the universe but remain poorly understood. The interactions that occur in these extra dimensions can provide the missing pieces to our understanding of how the universe behaves on both large and small scales. Finally, exploring the implications of string theory's extra dimensions opens up imaginative possibilities, such as the existence of parallel universes or alternate realities. It has plagued scientists and philosophers, inspiring us to rethink our concepts of reality and existence. Delving into these extra dimensions could revolutionize not only our understanding of physics, but our understanding of the universe in which we live. Higher dimensions, theories such as string theory suggest, can have a profound effect on the very structure of the universe and its large-scale structure. In a typical three-dimensional space, gravitational and electromagnetic forces operate within a limited framework. However, with additional dimensions, the interaction of these forces can undergo significant changes, which can lead to new forms of matter and energy. These dimensions can influence additional gravitational interactions that affect the formation and evolution of celestial bodies such as stars, galaxies, and clusters.